In this video, we are going to do some examples where we practice whether we need to trig sub or whether we don't need it. Okay, so for this first example, let's say I want to do the integral of the square root of x squared minus 16 over x. So first, maybe let's try a u sub on this. If I were to let u be x squared minus 16, which I think is maybe the most natural choice, then du is 2x dx. Then we typically want to ask ourselves, okay, do we see this derivative function in the integral? Maybe off, by this constant multiple. So let's ignore the 2. So do I see x dx in the integral? And the answer is not quite, because this is x times dx. And in my integral, we have dx divided by x, because that x is on the denominator. So as a result, this u sub, isn't going to be perfect for us. It's not going to be great. It turns out that if you carry this through, it's just not super helpful. I'd encourage you to do that for practice, but it just turns out it's not the most helpful. So the next thing that we might think of is what we've seen in the last couple of videos, that when you have a square root and inside of it you have perfect squares like this, either being subtracted or added, that's an indicator for trig sub. And we've seen that when you have a square root of something minus something, we typically make that side be a leg in our right triangle. But if you have a square root of something plus something, then you make that side be the hypotenuse. Okay, so for our problem, we have a square root of something minus something with those perfect squares. So when we set up our right triangle, let's make that square root thing be a leg. It doesn't really matter which leg we make it, so maybe I'll make it be this vertical one. And now to work out the other sides, let's do some Pythagorean theorem. So my first leg squared plus this square root leg getting squared should be equal to the hypotenuse getting squared. So squaring that square root will get rid of the square root, and I'll get x squared minus 16. And now I got to think about what goes in these other two parentheses so that this equation ends up being true. So this, I want to have you pause and try for about 30 seconds. So pause it in 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it to try it. So notice that is something that we have done in the last couple of videos. And each one, I've given you a chance to pause it to try it. This is one of the key parts of the problem. So it is very important to pause and try. So it turns out if you put a 4 here, this part becomes 16, and that cancels this minus 16. And then to make it work, we just got to put an x in this second parentheses. So if a 4 goes in the first one, an x goes in the second one. So the first leg should be 4. The hypotenuse should be x. Now I have to label one of the angles as theta. And it doesn't really matter which one, so maybe I'll just make it be this one at the base. So I'll have that be theta. And now I got to set up some trig functions for the different pieces of my integral. So on the numerator, I see this square root term. So I'm going to need some trig function that involves that square root term. And as we've seen over the last couple of videos, we typically try to do something involving that side that we care about, and then the constant side, so the 4. So I could either do tangent or cotangent. So perhaps I'll do tangent. So if I do tangent, I'll get the square root of x squared minus 16 over 4. Okay, and then if I rearrange that to isolate that square root, I get 4 tangent of theta equals that square root of x squared minus 16. So let me highlight this. So that means that square root term I'll be able to replace with 4 tangent theta. We also have this x on the denominator, so I will need some trig function that involves this x side. And I probably want something with the x and then something with a constant side. So I could either do secant or cosine. I'm going to do secant just because if I do secant, x ends up being on the numerator and it's easier to isolate for it than if I were to do cosine. But I could do either. So secant of theta is x over 4. And if I isolate for the x, we get 4 secant of theta equals x. Okay, I will highlight that. So x is 4 secant of theta. Nice. The only other thing we'll have to plug in for is the dx. To do that, I pick one of these substitutions and I take the derivative of it, whichever one's simpler. So this one looks simpler because it's easier to do the derivative of x than this square root term. So doing that derivative, we end up getting, on the left, I get 4 secant theta tangent theta d theta. On the right, I get 1, and then I got to put a dx next to it. And then I will highlight this. So dx is just 4 secant theta tangent theta d theta. So now we are ready to plug in. So I get the integral. My numerator just became 4 tangent of theta. I will highlight that. That's in green. That denominator, the x term, well, that was in orange. That is 4 secant of theta. And then finally that dx at the end, we've been highlighting that in blue. That was 4 secant theta tangent theta d theta. Okay, so we can cancel a little bit here. There's a 4 on the top and a 4 on the bottom that can cancel. That leaves me with the 1s. And then there's a secant of theta on the top and a secant on the bottom that can cancel. So that leaves me with 1s for both of those. So overall, this leaves me with, there's still a 4, and then I got tangent squared theta, d theta. In fact, just to make it a little simpler, let's pull the 4 in front of the whole integral. So I got this. So I need to know the antiderivative of tangent squared. Well, I know the antiderivative of secant squared, and there's a trig identity that involves tangent squared and secant squared. So tangent squared is the same thing as secant squared theta minus 1. That is just using a trig identity. Tangent squared is the same thing as secant squared minus 1. Okay, and now this is something that I can do the antiderivative of. So I got the 4 in front. The antiderivative derivative of secant squared is tangent theta. Antiderivative 1 is theta. Close the bracket. I need to put a plus c because this is an indefinite integral. And now I gotta sub back in. So I got that 4 in front. What's tangent of theta? Well, we had that over here. It's this square root term over 4. It's that square root of x squared minus 16 all over 4. And then for theta, to plug back in for theta, well, I got to use one of these substitutions and rewrite it involving the inverse function. So maybe let me do it using the secant one, just because there's no square root involved. This would be secant inverse. And then I swap the input and the output. So x over 4 is the input, and theta is the output. So plugging that in for theta, I get minus secant inverse of x over 4. Close the bracket, and then plus c. And we got it. And we got it. Okay, so depending on how we had set up the triangle, like perhaps whether we put the 4 here or the 4 here, like my trig functions that I end up with might look slightly different, but then what I end up getting at the end should be equivalent to what I have here. There's a chance that it might involve like slightly different inverse trig functions based on like how my triangle was set up, but it should end up being equivalent to what I have. One of the ways that we can, when doing problems like this, check like, oh, is my answer the same as what we're getting here if we had set it up differently, is we could plot this function in Desmos, and then if I'd gotten something different some other way, plot that function in Desmos to see, do the graphs look the same? Okay, so let us end with one final example. So let's say I have this function here, and I want to do this integral. Okay, so I will first want to have you pause the video for 3 minutes to try this one on your own. Probably not going to be enough time to finish it, but I mostly want you to be thinking about how do we get it started? What methods could I use? So pause it in 3, 2, 1, and try it. Okay, so hopefully you paused it and tried it. Let's talk about it. So we could make this work either way, with a trig sub or with a u sub. So u sub and trig sub will work. So typically if both work, I like doing u sub because it is usually faster. So the most natural choice for u sub is to let u be 4 plus 9x squared. Then du is going to be 18x dx. Okay, so at first glance, this might not look great because ignoring that constant multiple, I see x dx here. That's not quite what I see in my function because I see x cubed dx. But it turns out that if you persevere with this u sub, it will still work. If I rearrange this, I get du over 18 equals x dx. So when I start to plug in for this, I get integral. You know what? Let me also divide by the x. So I get du over 18x equals dx. And now I'm going to sub in. So I got x cubed over the square root of u. And then dx became du over 18x. And now the x's are going to cancel. I can pull the 18 in front. And I'll get integral of x squared root u du. The way I know that this is going to work still, though, is I'm left with x squared when I do this, but my u involves an x squared. When that happens, even if what I see in this function and my du aren't a perfect match, but if I realize they're kind of off, in this case, when I divide the two, I'm going to get like an x squared popping out. If that is what I see in the u, that's an indicator that, oh, if I persevere, this will work out really nicely. Okay, so let's continue to use this u sub, and let's isolate for u. So I'll get u minus 4 divided by 9 equals x squared. Okay, so I can plug that in. And then this divided by 9, I can pull it in front of the integral. So I'll get 1 over 18 times 9 on the bottom. And then the x squared, now for that, I'm left with the u minus 4 over the square root of u, du. And now this is much easier to evaluate because I can split up this fraction into 2. This becomes a u over square root of u, and then a minus 4 over square root of u, which is u to the 1/2 minus 4u to the negative 1/2. And now that's something that I can do the antiderivative of. Okay, so for this 18 times 9, we can work that out. Let's see, that's going to be 162. 162, and then I got the integral. Let's just do the integral. So this first term, reverse power rule, I'll get u to the 3/2 divided by 3/2. So I can multiply by the reciprocal, 2/3. And then I got minus 4. Again, reverse power ruling, I'll get u to the 1/2 divided by 1/2. But that's the same thing as multiplying by 2. Multiply by 2. Close that bracket. This is an indefinite integral, so I got to put a plus c. And then now I should just plug back in for u, and I can simplify a little bit. So I got 1 over 162 in front. And then I get 2/3 times, plug back in for u, 4 plus 9x squared to the 3/2. And then 4 times 2 is 8, so minus 8. And then plugging in for u, 4 plus 9x squared to the 1/2. Or if I wanted to write this as a square root, I could have. And then I got plus c, and we have it. Okay. So I mentioned at the beginning of this that this one is also doable with a trig sub, because I see a square root and perfect squares inside that are getting added together. So I could do a trig sub. If we did a trig sub, we should end up with the same answer as this. Remember, if it looks slightly different than this, that might be because maybe I'd set it up slightly differently with my triangle. But it's always good to then check, like, okay, if I plot this in Desmos and I graph it, and if I did it a slightly different way, if I plot that in Desmos, do the graphs look the same? And that's an indicator that, okay, they actually are equivalent.